I hope all of you are doing well. I am Mr. H. Thank you for joining me for this video. Limit as h approaches 0 f of x plus h minus f of x divided by h. What does this mean and represent? It is the basic definition of a derivative which will give you the slope of a curved line at a particular point. Consider this simple representation. I have a linear function, a straight line, angled at a certain direction, but it's still straight. I have a point over here and I have a point over here. This point would be x1, y1. This point right here is x2, y2. I want to determine the slope of this line, and it's easy. We have a formula. Slope is equal to y2 minus y1 divided by x2 minus x1. When the line is straight, this is what you utilize, and we'll put this over here for our reference. Slope of a straight function, a linear function, would be y2 minus y1 divided by x2 minus x1, change in y divided by change in x. The picture is vastly different when the function you're looking at is curved, meaning it's non-linear. Now let's look at this representation. I have a function which looks something like this. It's no longer straight. I want to determine the slope of this function at a particular point. What do? Well, I can use the concept of slope and modify it to give me a slope of this function at a particular point. I have a specific point over here. We'll call this x. Certain units away, h units away, I have another point. This right here would be x plus h. If this was right here 2 and I'm looking 5 units away, it'll be 2 plus 5. This would be 7. That's exactly what we're talking about. When I'm looking over here and across, I'm looking at their y values. What is the y value over here? Obviously, it will be whatever your function is. What you put into it and what you get out. What you put into it is your x value. What you get out of it is your y value. This point right here would be x comma f of x. That's what it is. This point right over here would be exactly an x and a y, but your x over here would be x plus h, because now you're looking at a point x plus h, and your y value would be that same point put into your function, and it would become f of x plus h. Now you have x f of x, x plus h, f of x plus h. These are basically your x1, y1, and x2, y2. Run this right here through that basic slope formula. What do you get? You have m here is equal to f of x plus h minus f of x. This right here represents my change in y divided by change in x, which is x plus h minus x. That's my x2 minus x1, change in x. But what is it telling us? When we're using this formula, we're using the formula for a straight line, a linear function, which means we're connecting these two. But if we're doing a slope of a curved line using a straight line, we're not getting a proper slope at a particular point. What we're getting is like an average slope. Between these 2 points, what is the average slope? This is what it's giving us. What you have to do is modify this, because this right here is the point I'm interested in, and I want to determine at this particular point what was the slope. And this right here is a symbol for slope m. What is the slope at that particular point? So now I have to start modifying my representation right here so I can get to a derivative at here. And how will I get to that derivative? I still need 2 points if I'm going to use this formula right here, but I'm going to modify my second point and bring it closer and closer to my original points. That way I will end up with 2 coincident points. If I draw another point over here less than h units away, but I'm still some units away, but slightly I'm closer, I can draw another line, and these are secant lines. Secant lines connect 2 different points. And now I can draw yet another point over here and then connect up, and I've drawn another secant line. What I'm doing is slowly decreasing the distance from my original point, my latter point, bringing it in closer and closer, so my secant lines are becoming closer and closer to a tangent line. The tangent line is what will give me the slope of this function at a particular point, and the slope of a tangent line is given by this formula over here. When we do the slope of a tangent line, what was I doing? I was converting secant lines to tangent lines by reducing the distance from x and x plus h. By reducing this distance, this h distance right here was being reduced. And how do I capture that in terms of a formula? It's by this part right over here. I still have the same formula, the slope of 2 different points, and you're seeing that. But now I have to capture this decrease in distance, and that's where I'm going to bring in this limit. The limit as this distance is decreased, meaning the value h is reduced, meaning delta h. From here to here I have a certain delta h. As delta h becomes closer and closer to 0, we are bringing it by means of this limit. This basic formula for a slope of a straight line will then adopt the slope formula for a curved function at a particular point. All you have to do is just simplify this. When you simplify it, you end up exactly where you need to be. You have f of x plus h minus f of x. This x and this cancel out and you have divided by h. So this right here represents the slope of a curved line at a particular point. And that particular point happened to be here. I was using secant lines and slowly bringing them down to a tangent line. In my tangent line, I have a point right here and I'm connecting it to the same point on top of each other. Two coincident points, a line at that particular point will be my tangent line, and it is represented by this. This part right here, limit as h approaches 0, is clearly telling you your second point has come on top of your first point and now you've developed a tangent line. If you solve this out by means of whatever the function you have, then you will have determined the slope of your function at that particular point. Look over here at this function x squared. I want to determine the slope of this function at point 3. If I were to just do with the basic slope formula which you see right over here, I can pick a point over here and point over here, and let's call this 1, let's call this point 4. It's not drawn to scale, but imagine it is. When I look at this point, I know what it is. It's 1 comma 1, because I put 1 here and x squared, I get a 1. By this other point right here, which is a 4, I'm looking here at a secant line. I'm determining the slope of that secant line. I put 4 over here because I'm looking up and then across. I do 4 square, I have 4 comma 16. Now I run this through the slope formula, y2 minus y1 divided by x2 minus x1. I have 16 minus 1 divided by 4 minus 1. And here I have 15 over 3. And what is this giving me here? It's giving me the slope of not your function at a particular point, but it's giving me the average slope of this function over this domain 1 to 4. And 15 divided by 3 is giving me a slope of 5. This may be accurate or it may not be accurate, but most likely it will be inaccurate because I'm interested here at a slope of this function at point 3. I would have to actually carve out a tangent line and determine the slope of this tangent line, and we can using that formula. We have this formula now, so why don't we utilize it? We are doing derivative of this function x squared using this formula, and I have to run it through this formula right here. I'm going to do x plus h whole square, limit as h approaches 0, minus x squared, which is your function. This is my f of x plus h accommodating this x squared. This is my f of x divided by h. All I have to do is open this up. I'm doing x squared plus 2xh plus h squared minus x squared divided by h. These cancel out. What remains over here is 2x h plus h squared over h. I can isolate an h. I'll have a 2x plus h divided by h. These cancel out and I'm left here with a 2x plus h. Limit as h approaches 0, this will 0 out, this h will 0 out, and I'll only be left with 2x. Now how do I actually determine the slope of this function at 3? I just do 2 times 3. I will run it here. 2 times 3, and the actual slope at that particular point is a 6. What was I getting using that average rate of change? I was getting a 5, and you knew that was not 100% accurate. The accurate slope is 6. So this right here is a means by which you can determine the slope of a non-linear function at a particular point using the concept of derivatives. Thank you for watching.